Hi, my name is Max Ditson, and this is my Lab 5 for Physics 2212. So, what are we going to be doing today? Well, for today's experiment, we're going to observe the interaction between a falling magnet and a tube of aluminum foil. The purpose for this experiment is so that we can apply our knowledge of Faraday's law to a real-life application, and so we can observe the effect of magnetic forces on ordinary objects. Here are a few of the physics principles we're going to be using today. The first one's going to be Biot-Savart law. This law is just going to help us find the magnetic field that we produced. Faraday's law is also going to come into play today, as is the name of the lab. Faraday's law just says EMF is equal to the change in flux over the change in time. And of course, Newton's second and third laws will be coming in today, where the second law says force is equal to mass times acceleration, and the third law, which states that every action has an equal and opposite reaction. So for the experiment itself, we did have to assume something, and that was that we were ignoring air resistance. We wanted to use our force equals mass times acceleration equation, and that would involve the magnetic forces and the gravitational force. And calculating the air resistance, what that would have been a hassle, so we're just going to assume that it's negligible. We're also going to say the system of our experiment is the magnet and tube, while everything else is the surroundings. And then for the experiment itself, we simply just dropped a falling magnet through a tube. We had a friend of mine who recorded it. We did this 5 times. And when we looked at the recordings afterwards, we were able to figure out how long it took for the magnet to travel through the tube. And for that time, we got an average time of 0.77 seconds. Here's some of the code for the computational model that we created. These two are functions that we create ourselves. The first one is calculating the dipole using the Biot-Savart law we said earlier. And the one on the bottom is calculating the flux of the falling magnet. Now this big while loop is what's going to be setting up the main experiment. This while loop is going to set up the computational model to represent the falling magnet through the tube, and it's also going to be setting up a nice velocity versus time graph. So we had to plug in some stuff here for us, mainly just finding the gravitational force, the magnetic force using Biot-Savart law, and using the flux equation that we calculated earlier, just to set this all up nice and neat. And here's the end result of our code. As you can see on the far left, we have a visual representation of our magnetic tube. Unfortunately, we do not have a video, but this is just an in-picture demonstration of what it would have looked like. The blue ring at the very bottom is representing the magnet, and that was at the very end of the tube. On the right, we have the velocity versus time graph, just checking what the velocity looked like at different times. And we also were able to figure out the time that the computer predicted based on the measurements that we got, and it was about 0.845 seconds. Unfortunately, these two times did not match up together. Our computational model predicted a time that was greater than the one that we were expecting. So some source of errors that could have gone with this was the fact that we ignored air resistance. It was one of our assumptions. Air resistance would have affected our Newton's second law equation, so that would have been a big difference. And there's also human error. One of the big things we measured was time, and we were looking at a video to figure out when it crossed. Instead of having pinpoint accuracy, we were kind of eyeballing it. So there's a very high probability that the time that we calculated was off. We also had some questions that we wanted to answer after the experiment. The first one is, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The current induced in the tube would be much greater as there is less resistance. This would cause the magnetic force to be much greater, and since that force is acting upon our falling magnet, the magnet would fall a lot slower. There is a chance that the current induced would be so great that it could even stop the magnet from falling altogether and perfectly balance out the gravitational force. And our second question is, what if holes or slots were cut into the tube? How would this affect the ring currents of your model? So cutting holes into the circuit would cause the current to alter. Instead of like a straight through current, it would be all over the place, dodging around the different holes. These holes would somewhat stop the flow of the current, not completely, but enough to decrease the magnetic force, and due to that reduction of magnetic force, the magnet would fall a lot faster. And yeah, thanks for watching.